Okay, so I wanted to look at our next section, which is parametrics, and parametrics is another one of those I think really cool topics, and it's another lens that we can start analyzing relationships that may not necessarily have been functions in the normal XY world, but when we add an extra parameter, which is usually time, we can represent these curves as functions. And so, in terms of like a definition of a parametric equation, like in our notes here, let me go ahead and switch to the smaller ink here. Okay. So, for my definition here for parametric notes, like for us, we're just gonna have x's and y's. So it's going to be two equations or a set of equations. Oops. Try this one more time. Pen. And there we go. So a set of equations that include a parameter. Now, our parameter is usually time. And that's why it's called a parametric. The metric is referring to time here. Okay. And so it's going to give us a position as an x-coordinate of time and a position y in terms of time. So we're going to need two equations. So a lot of times you might say like x of t equals something in terms of t, and y of t is equal to something in terms of t. And you need both of those together. And so like as an example, it might be like x of t equals t plus 1, and y of t is equal to 3t minus 5. So what I can do is I can say, okay, if I want to know the position, like what's the xy coordinate at any point in time, then that's what I'm going to let t equal. So like at t equals 0, for this just kind of like this made up thing here. So at t equals 0, where did the point start on the xy plane? Well, when t is 0, the first value for x is 0 plus 1, which is 1. And then when t is 0, you get 3 times 0 is 0, minus 5 is negative 5. So I know that at time equals 0, the point's at 1 comma negative 5. So if I were to graph this, again, just off the top of my head on a Thursday morning here, 1, negative 5, I would know that at time equals 0, that's where I find my point. And if I wanted to know what's time equal to 1, well, at 1 plus 1 is 2, and so I know the x component would be 2, and then 3 minus 5 is negative 2. So then I would know that it would have gotten to here. So like t equals 1. So I went from here up to there. And so we're starting to describe this curve, not only on its position, x and y, but also on time, like when is it there? And so automatically my head is thinking physics, right? Because like physics, we relate position, and the change of position over time is velocity. And so as you go into calculus next year, these are going to be interchangeable, in terms of analyzing parametric functions with time. And that obviously is a good application for velocity. Okay, so let's look at the first example that we have here. It says a particle is moving along a curve, and when you see the word curve, it may not necessarily be a curve. It could be a straight line. It could be a vertical line. It could be a non-function. It's used very loosely to describe the path. Okay, so when you see that word curve, just kind of expect that. That is described by these parametric equations. Sketch this path. I like how I use that, like synonym there. From 0 to 10. Okay, so it might be worth our while to make a little chart, in terms of like when t is 0 through 10, what is our x value, what is our y value? And so it's a little bit, it's not hard, just a little, tedious. So time equals 0. That's our initial position, by the way. When time equals 0, we get 6 and we get a 10. And then time equals 1, we get 5. And we get, oh, lovely. Let's see, 8.5. When time equals 2, we get 4 and 7. When time equals 3, we get 3 and 5.5. Now, I'm already seeing the pattern. X's are decreasing by 1, and the y's are decreasing by 3.5. And that should, I guess in hindsight, be no surprise, because the relationship between time and x and time and y are both linear. So as soon as you find your initial spot, you don't even have to necessarily plug it in if it's linear. We would know that at time equals 4, this is 2, and then this is 4. Sorry. When time equals 5, this is 1, and this is 2.5. When time equals 6, this is 0, and this is 1. When time equals 7, this is -1, this is -0.5. So we're decreasing 1.5 each time. When this is 8, this is -2, and this is -2 as well. And then we have 9, this is -3, -3.5. And when this is 10, this is -4, and this is -5. Okay, so here are all the different positions, and starting at time equals 0. So I might want to put that on my coordinates here. Time equals 0. We're at 6, 10, which is like right here. And then time equals 1, we're at 5, 8.5. And time equals 2, we're at 4, 7. At time equals 3, we're at 3, 5.5, my bad. And, I probably should be labeling, this is time equals 1, and this is time equals 2, and time equals 3. And then, etc. So time equals 4, 2, 4. And then we're at 1, 2.5. And then we're at 0, 1. And then we're at -1, and then -0.5. And then -2, -2. Oh, this is fitting perfectly. How nice. -3, -3.5. And our last one, -4, -5. Now, just right there. Okay. So, and this is where time equals 10 is. And the thing is that time is continuous. So it's not like just these discrete points, but it continues, so it's, every instant between 4 and 5, it's moving along this path. And so then I just kind of want to connect them. And here's again, it's describing sort of like the motion here. There's nothing that, exists before here because our parameter is only from 0 to 10. So I would just connect down. And I'm really not drawing a straight line very well this morning. That's okay. Go back down here. And then it stops. So it's really just a segment. And we certainly could draw in arrows to indicate the direction if we didn't have like t equals 0, t equals 1, t equals 2. So again, very useful to help describe a path, help us describe motion. So it's not just where is it, but when is it there? And so that's our path of that particle. Okay, now sometimes I might say eliminate the parameter. Like what would this look like without the time, right? So it's not too hard to eliminate the parameter when they're both linear. I'm anticipating a linear function, and remember usually a linear function is like y equals mx plus b, and notice there is no, there's no time here. So it's very helpful to say, okay, if I know x is equal to 6 minus t, then I can just solve for t. So t equals 6 minus x. So I'm just solving for the variable t. And then let's just substitute that in to our other equation. So if y equals -3/2, and instead of putting a t, we're going to write 6 minus x. And if I distribute that, so y equals -3/2 times 6, I don't know why I did that, plus 3/2 x. And so then that's 3/2 x. And then that would be, -9, is that right? Did I do my math right? I'm putting that in plus, oh, sorry, I forgot. my plus 10. I was like, that's not the right intercept. But negative 9 plus 10 does give me the right intercept. Plus 10. So that's negative 9 plus 10 is 1. So y equals 3/2 x plus 1. So this would be the line without the parameter. I've eliminated the parameter. There's no more time. But I can see an intercept of 1, which is here, and I can see a slope of 3/2. But notice this doesn't tell me any kind of direction. It doesn't tell me where it's at that particular time. Okay, so let's do this curve as well, in just from 0 to 4. So, again, thinking about, like when in doubt, and that's why I tell my students who are getting ready for this AP exam, when they see parametrics, when in doubt, you could always make a table of values. So time equals 0, time equals 1, time equals 2, 3, and 4. And then our x position starts at -2, and the y position starts at -1. And then when I put in 1, 1 minus 2, so that's -1. 1 squared is 1, and so then we have half minus 1, which is -half. 2 minus 2 is 0. 2 squared is 4. Half of 4 is 2. 2 minus 1 is back to 1, or up to 1, I should say. 3 minus 2 is 1. 3 squared is 9, and then half of 9 is 4.5, minus 1 is 3.5, and then 4 minus 2 is 2. 4 squared is 16. Half of 16 is 8. 8 minus 1 is 7. So our x component is still linear, and again, no surprise because our relationship was linear. Our y variable is actually quadratic in nature, so it's a different kind of example. It's okay. We'll still start. So -2, -1 is our starting point. So x equals -2, y equals -1. That's when t equals 0. And then let's see, we have -1 and then -half. -1, -half. And then we have 0, 1 here. So our rise is going much quicker. 1, 3.5. 1, 3.5. And then 2, 7. So 2, 7. And so then if I graph this path, starting at t equals 0, t equals 1, t equals 2, t equals 3, and t equals 4. And again, time being continuous. So then I'm starting here and going up in that direction. Again, showing arrows to indicate the path. And it does look quadratic, and the path looks quadratic. And if we eliminate the parameter, just like we did before, so if x equals t minus 2, then plus 2 is equal to t. And if I sub that here for t squared, so y equals 1/2 quantity, x plus 2 squared minus 1. How convenient. It's already vertex form of a parabola whose vertex is at -2, -1, and then opens up, and we can see that path. So it's relatively easy when the functions are quote unquote basic to eliminate the parameter. Okay, so I think that will be a good spot for the first video. So you got a chance to kind of look through some of those. So I'm going to pause this, and maybe you can try a couple of examples, and then we'll just keep going through more and more problems.